Okay, in this video we're going to go over Chapter 11, Ratios and Rates. So what is a ratio? A ratio is a comparison of any two quantities. Okay, a ratio can be used to convey an idea that cannot be expressed as a single number. For example, this harvest example tells you about density. So if you get the same denominator, so right now you have 4,000 cars to 3 square miles compared to 3,000 cars to 2 square miles. If you get the same denominator, so make both the denominators 6, what we're going to do is we're going to be able to compare these densities, okay, and that's going to be times 3. So once you have it in this situation, we can say that this density is greater. So at Harvest Festival in Town B, there's a greater density of cars. Ratios can also compare measures of the same type. So part-to-whole comparison. So for example, if you want to say that there are 5 girls in every class, you can write it like that. But then this is a part-to-part comparison. So we can also say that there's 5 girls for 6 boys. Okay, part-to-part and part-to-whole are different, so be aware of that. When a ratio compares measures of different types and is conceived of as describing a quality that is common to many situations, it becomes a rate. So the thing is, it has to be common to many situations. Important points: in some ways ratios are like the other interpretation of rational numbers, but in some ways they are very different. Okay, ratios are not always rational numbers, but part-whole, operator, measure, and quotient fractions are always rational numbers. Ratios may have a 0 as their second component, but fractions clearly cannot have a denominator of 0. A fraction is an ordered pair. That is, if you reverse the order of a to b in the fraction, you have a very different fraction. Ratio arithmetic can be very different from fraction arithmetic. Okay, so ratios and fractions, they're not always interchangeable, so just be aware. Notation and terminology. A ratio is sometimes written in fraction form, so you can say 3 to 2, or you can say 3 to 2. But part-whole comparisons, operators, measures, and quotients are usually written in fraction form. The ratio of A things to B things can be written several ways, and I've included 3 of the 4 ways here. There's a 4th way that I had never seen before, and I didn't even know how to type it, so I didn't have a math type that allowed me to do that, so I have not included that here. When dealing with ratios, if the fraction form is used, include the quantities as well. That is, if the ratio of girls to boys is 5 to 7, you want to write it like this so that it's clear what you're talking about. Okay, let's go through some of the verbal interpretations of A:B. So you can read that as A to B, A per B, A for B, A for each B. For every B there are A. The ratio of A to B, and A is to B. So there's many ways that you can speak this ratio. Often ratio language is used as an alternate way of expressing a multiplicative relationship. So if you say there are 2/3 as many men as women at the concert, you can express that this way. It's not additive, it's multiplicative. Okay, and then I said again, to distinguish this comparison from a part-whole comparison, we can write 2:3. The ratio of men to women is 2 to 3. Okay, equivalence and comparison of ratios. Okay, so think about this. The part-whole comparison here is 2 black triangles to 2 of the triangles are black out of the 3 triangles that are present. Okay, so that's part-whole comparison. The ratio interpretation is 2 black triangles to 1 white triangle. So you want to know what it is you're trying to express. You can compare ratios by SSP, which is when you create the same denominator, and by SNP, same number of parts, where you create the same numerator. Okay, so let's see how we're going to do that. Okay, if you're going to compare 3/4 to 5/8, This was done incorrectly in your textbook, so I'm going to do it correctly here. So you can compare by a process called cloning. So a 5 clone of 3 to 4 yields 15 to 20. A 3 clone of 5 to 8 yields 15 to 24. So you can see that given that comparison, you are now able to have the same numerator, if you will, the same first term, and then you can compare it to the second term. If the second term is bigger, then that value is smaller. So therefore we can state that 3/4 is greater than 5/8. So in terms of cloning this, so this was a 3 to 4 right here, and we cloned that 5 times, so that's why we wrote it down like this. This was a 5 to 8 clone here, ratio here, and then we cloned it like this. So that's going to let you compare it now. So what if we wanted to compare these same two fractions using same size parts, same denominator? So get the same denominator. This is an easier procedure because you only have to do an operation on the first ratio. So what we did was we did a 2 clone. So 2 times 3 is to 4, and we got 6 is to 8. And then we were able to compare that to 5 is to 8. And so we're still finding, though finding it quicker, that 3 is to 4 is greater than 5 is to 8. Remember that ratios are relative comparisons, one thing to another. So let's try some ticket comparisons. Which would be better? Which would be a better deal? 2 tickets for $3 or 5 tickets for $6? So you're going to have to equalize. I chose to equalize the denominators here. So if I multiply the first ratio by 2, that ends up being 4 to 6. So now I'm comparing 4 to 6 to 5 to 6. Remember, we're talking tickets to money. Okay, so more tickets for the same money in case 2 is a better deal. So the 5 to 6, this is a better deal. This solution can be represented mathematically this way. So do your 2 clone, subtract, and this is telling me I'm getting fewer tickets for the same money. So therefore, the second deal is better. So you can view it either way. Okay, ratios as an instructional task. So classroom discussion of ratio situations should focus on these questions. So in addition to the explicit facts, what else do I know about this situation? Does it make sense to reduce the ratio? Can the ratio be extended? If I extend or reduce this ratio, what information is gained or lost? If I choose a smaller or larger sample, will the ratio apply? And what is the meaning of a divided ratio? So see page 233 to page 235 in your textbook for examples of all of these. Okay, what is a rate? Okay, remember a rate is an extended ratio. So it can apply to more than one situation. So, for example, gas prices, that could be viewed as a unit rate. Rates can also be thought of as a description of the ways quantities change with time. They are identified by the use of the word per in their names, and they can be reduced or divided to a relationship between one quantity and a unit quantity of the other. And when you do that, that's what's called a unit rate. Rates may be constant or varying. It may be mathematically possible to extend a rate, but this does not mean that it always makes sense to do so. And some rates are reported as single numbers. Operations with rates and ratios. Okay, ratios and rates often do not behave like part-whole fractions. So for example, if you're looking at a basketball player and he makes 6 free shots, he shoots 6 free shots and makes 4 baskets. Later in his practice, he takes another 6 shots and makes 7 of these. How can we describe his performance for the day? Okay, so what you're going to do is you're going to add these ratios. You would never do that this way if they were fractions. All right, so they sometimes operate like fractions, but not always. Okay, linear graphs. A ratio may be mathematically extended or reduced. The results of this action yield equivalent classes. And I thought it was pretty clever to put them on a linear graph. So if you look at page 239 in your text, you'll see that. And so putting it on a linear graph, you can figure out very quickly which classes are equivalent and which are not. Okay, so let's see where I was. A constant number that does not change. Okay, so let me come back up. Okay, so when they did this and they put the ratios on a line, what they saw was that if they are equivalent, they will have their corners on this line. Notice the second one that I drew is slightly up, so therefore that's not equivalent. So that's a nice technique. So reading the rest of these, I'm going to leave that up to you. And let's go down comparing ratios and rates graphically. If classes are equivalent, they'll appear on the same line, just what I just said. Okay, one of the most important rates we work with is speed. Most high school students don't realize the speed is a composite quantity, the comparison of a distance to a time. So distance equals the speed, miles, times the time, hours. And therefore, speed equals distance divided by time, or miles per hour, for example, or kilometers per hour if you're in Canada. Okay, students' misconceptions about speed. So this is another thing about averaging things. So if they tell you in a problem that Juan drove 20 miles per hour for 1 hour and then increased his speed to 40 miles an hour for the last 2 hours, what was his average speed? Okay, many younger high school students will just grab the two numbers that they have in the equation, the 20 and the 40, and they'll add them and divide by 2 and get 30. But that's not accurate. So you have to consider how far he drove. So how far did he drive? The first hour, he was going 20 miles an hour, therefore he drove 20 miles. The second hour and the third hour, he is driving 40 miles an hour, so you're going to add 40 and 40. That gives him a total distance of 100 miles that he traveled in 3 hours' time. So his average speed ends up being not 30, which we got if we said 40 plus 20 divided by 2, but a little bit more than that, 33.3 miles per hour. Okay, average speed, in relation to speed, when we use the word average, it means distributed proportionally. It does not refer to an arithmetic average of these individual speeds in isolation. Okay, here is a distance time graph. Okay, these are great for discussion purposes in your classes, and it's a nice way to understand this concept. So you can tell a story about each of these graphs. So the green one, it's a quick, steady speed, constant slope. Okay, the blue one, you started out a little bit slower, and then you start getting faster. It's a changing graph. It does not have a constant slope. Okay, the red one is interesting because you have a story going along with this. You initially travel from this point to whatever time this is going to be at a steady rate. Then you don't travel, but time still passes. And then what do? You're traveling a negative distance. You're traveling back home, and you're going to end up back at the start. Okay? So your displacement, which means the distance away from your starting point that you are at the end of your journey, is 0 with the red case. You see that? Because you're back at the start. But your distance traveled is the maximum on our graph for the green case and the blue case. Okay, I really liked this. I got it off the internet, and I know it's a little blurry, but I think it's worth discussing it. So here are distance time graphs, and so the story behind the first graph is a student walks from home to school at a constant rate. Okay, so now look at the next graph. This time the student's walking from home to school. He stops and has a conversation. He stops at the convenience store to buy something. So he goes into the convenience store, time passes, distance does not, and then he resumes walking. Okay, the third one, a student is walking from his house toward the school. He hears his friend calling from behind, and he heads back to meet him. Okay, notice the slope goes negative because his displacement is decreasing. He is going back towards where he came, and it's taking him some time to do that. Okay, and then he's going to continue walking once he stops going in reverse, basically. Okay, the 1, 2, 3, 4, fifth one. A student's headed to the bus stop, and then he sees the bus, and so he accelerates. So initially he's going pretty slow, and then he has an exponential response to the fact the bus is already there. Okay, and this next one, a student's walking to the cafeteria for lunch. Okay, at this point right here, at the peak, he's just back at the cafeteria, and he realizes his money fell out of his pocket. So he has to retrace his steps, so he's going backwards. He stands there for a little bit looking around. He finds it and then starts heading back to the cafeteria. And that's the path he takes, another constant speed. Okay, final notes. Velocity is a vector composed of both speed and direction. So you can say we traveled, our velocity was 30 miles per hour and we traveled due east. Okay, so velocity has both speed and direction. And displacement, which is a term I've been using, tells how far you are from your starting point. Okay, so that ends this chapter, and you now can go back and look at the activities and look at the problems in the problem set that pertain to this last chapter.